So last time we basically finished the Schwarzschild spacetime, the global structure, and the beautiful interplay between physics and geometry of the crustal extension of the Schwarzschild spacetime. And so, just from last time then, the crustal extension. So we saw that the global picture of the structure of space-time is that we got this line u equal to 0, v equal to 0, these are crustal times up here, and then we got a singularity, and so the singularity here is this, r equal to 0, u times v equal to 1, this is the singularity up here, and this is an asymptotic region. This will be the black hole region. This is another asymptotic region, and this is a full crustal extension we saw. And I mentioned at the very end that, however, this is the mathematical extension of the full Schwarzschild space-time. In classical general relativity, we don't expect it to be realized in nature. We expect that you are given some initial data, like a star or something like that collapses and forms a black hole. And therefore, there really isn't a white hole region. There's only the asymptotic region, the black hole region. So if you actually have a collapse, then the picture is that you've got a star up here. You know, the star is, so this is the world line of the star, the world tube of the star. So star is something like sitting up here, the world tube of the star. Time is running like that, and this is sort of the spatial cross-section of the star. And then at some stage, the star collapses. Star collapses and forms a singularity. So this is like our r equal to 0 singularity over there. We use the same chalk, same color. And then the statement is that there is a corresponding horizon that is formed. So this is like the u equal to 0 line. So, and then this region up here will be the black hole region like that. And this region is just an asymptotic region. So from here, the signals can go, the light rays can go out. So this is the outgoing light ray. And then there are infalling light rays. Infalling light rays will fall into the singularity. The outgoing light rays will just go out to infinity. So only the region, so this is the only region 1 up here, and region 2 will actually be realized in nature. This is just a mathematical extension of the region 1 that we got. So that is the situation with classical general relativity. The idea is that you're given some time t equal to 0 up here, some initial data, and we evolve. This is r equal to 0. This is some star radius r equal to r0, but this r0 depends on time because the star collapses. It collapses, reaches 0 radius, makes a singularity, and this is the kind of picture that we'll have. So these two are considered to be mathematical extensions, do not have direct physical meaning. On the other hand, in many quantum field theory considerations or considerations that involve black hole thermodynamics and so on, one often considers the total global region that we have got. All right. So now, what we want to understand, today's talk is really about the next topic, I think it is topic 4. Topic 4, which is what is a black hole. So we just saw this one's simplest example, and now we want to know what is a black hole in general. So the idea is it's the same that we saw before, namely, we'd like it to be the case that there's a region in space-time from which causal signals cannot be sent out to infinity. That region is what we would like to call black holes. So, for example, the same picture now I draw, the collapsing star picture, I draw here. All these pictures you will see in books and papers, so it's good to be familiar with them. So the idea up here is, again, I got some star. So this is a world tube of star. So this is the world tube up here. This is what the ball here is what the star looks like at an instant of time. And then the star actually time is running like that. Say coordinate time is running like this, and space is these cross sections. These two directions are space, and this is time. This is the kind of the time coordinate, so to say, is running. And here, this is star is static, and here picture is very much like Minkowski space. This really is a time-like direction. This really is space-like section and so on. But then supposing the star actually undergoes a collapse, okay, and therefore this is r equal to 0 now. R equal to 0 line was that. This was the radius of the star. It collapses, forms a star. R equal to 0. And then there is a singularity. So in this picture, different from this picture, singularity really is going to be space-like. But in this picture, we're not worrying about space-like, time-like character. This really is just a coordinate time. And then this was r equal to 0 line. So in coordinate picture, this r equal to 0 line would just look like that. This would be r equal to 0 line. So this really is a much more faithful diagram, because you see that space-like line is really space-like. Here should not, this is not faithful for the causal structure of space-time. This looks like a time-like line, but it's actually space-like. It's just a coordinate time, so r equal to 0. And then the statement is the following, that supposing this is what happens. Then what happens is that if you are very far away from the star, then the metric is going to like a Minkowski metric. And as you know, in Minkowski metric, space-time, the light cones are just like that. At any point, there is a future light cone, there is a past light cone. These are the light rays that are emitted and so on. But as you come closer and closer to the star, because of the gravitational attraction of the light rays, these light cones start bending until there is some surface that is formed. And this surface is again the horizon. So this horizon is really this surface up here, which is the horizon, is the analog of this surface up here, horizon, or this future horizon up here. Because you've got both a black hole and a white hole, there's a future horizon and a past horizon. For black hole, is relevant, this is future horizon. So this horizon is like that. We know that every point up here is a two sphere, and here it is a little bit more manifest. So you see that this is, of course, it looks like a circle, but for one dimension suppressed, so it looks like it's a two sphere. So that is a horizon. And then what happens is that as the light cones start tipping, as we come closer to the star, light cones tip. Out at infinity, they are straight, like in Minkowski space. So light cones start tipping, and then here the light cones just tip completely. So all the future directed light rays are directed like that towards the singularity. So they don't escape to infinity. All the future directed light rays are trapped in this particular region, and this region is then the black hole region. Because for any point up here, the future directed light rays are not going out. Or here, this is going in, but this is going out. This is outgoing. Or here, the outgoing light ray is like that, and the ingoing light rays are like that. So all of them are trapped in this region. So this region up here is black hole region or trapped region. From which causes signals will not be able to escape. So that is what the intuitive picture is. There's still a heuristic intuitive as to what is the black hole region. Well, it's a region from which causes signals will not go out to in the asymptotic region. But to make this whole thing precise, we need a notion of what you mean by asymptotic region. So the key question now is, what is asymptotic region? And that is the big digression that we have to make in order to define black hole, to define precisely what asymptotic region is. This notion was introduced already in the 60s by Penn around 65, 67. And And this notion of asymptotic, what do you mean by asymptotic region, asymptotic flatness, and so on, is important, plays important role in many, many different contexts. It's going to let us define what a black hole is. It is also in the context of quantum black holes. This is also enables us to define what you mean by S matrix. And one of the fundamental questions about quote-unquote information loss in the quantum evaporation of the black hole is whether the S matrix is unitary. And to define S matrix, we have to define Hilbert spaces of asymptotic states. And again, this notion of asymptotic region is what is used. And quite apart from black hole classical and quantum black hole region physics, this notion of asymptotic flatness is a bedrock on which the entire theory of gravitational radiation and gravitational waves underlies. So when people do numerical simulations, what they are trying to achieve is really these asymptotically flat spacetimes, and then as we're going to talk in a minute about certain boundaries of these asymptotic spacetimes. That is where the gravitational radiation is actually extracted in a meaningful way. So it plays a role in many, many different contexts, and that is why I want to take a little more time to explain this in some detail. So this is what we now want to talk about. What is asymptotic region? So this is the notion. So again, to get our intuition straight, we always start with Minkowski spacetime, which we have good intuition about. And then in this Minkowski spacetime, of course, all flat, but still, we would like to know what is asymptotic region, how do I do physics there. For example, I may have Maxwell fields in Minkowski spacetime. We would like to talk about what is radiation, how much energy is carried by Maxwell fields, and so on. And that is all made much more precise in terms of this construction due to Penn. So in Minkowski spacetime, the standard metric is just given by minus dp squared plus dr squared plus r squared times the angular part. And what we are interested in Minkowski spacetime is to go in the faraway region in the null direction. Because for black holes, it is because you want to know, in fact, which part of space-time is visible from infinity, and to know about which is visible from infinity, what we need is to go away in the null directions up here. If you are looking at radiation, again, roughly the radiation propagates in the null directions, and therefore again, if you take a ride on the light front, that light front will take you to in the asymptotic region in null directions. So therefore, what we introduce is this future directed null retarded null coordinate, u is equal to t minus r. So u equal to u naught, r future null geodesics, or u equal to u naught, and then theta phi, so constant. These are future null geodesics. These are lines. U equal to constant is a line. If you just allow theta and phi both, then u equal to constant will give you a null point. So if I got a point in the Minkowski space, then u equal to u naught will be this null cone, future directed null cone. And therefore what you want to do is to keep u constant. So if I take this point and go further in time, so time is again running like this in the Minkowski space. If I take a future directed, another point up here to the future of the first point, then so this is point 1, this is point 2, then again I will get so u equal to u1. So this point is say naught and this point is say 1. So this will be u equal to u naught, this u equal to u1. That's going to be again another light cone that goes out like. So u equal to constant are these null cones and the idea up here is that we are taking a ride along these null geodesics, going in all possible directions, and we want to know where do we reach. And the point about this construction is really, so to say, we would like to look at where do these null geodesics end, so to say. So where do they find the resting place, the final resting place? Now, of course, in the physical space-time, there is no final resting place. As you go along here, r is going to infinity, and you just go u equal to constant, and r going to infinity, right? So you arrive at r equal to infinity thing, which is at infinity. But the whole idea of this construction is that we want to bring this infinity at a finite distance by conformal transformation, by rescaling of the metric. And if you bring it to the finite distance, so that infinity becomes a boundary to the physical space-time, then we can do local differential geometry on this boundary. And instead of taking limits r equal to infinity and worrying about whether some differentiation will commute with limit and so on, finally we're just going to be able to do local differential geometry on this boundary which represents r equal to infinity. So we want to bring r equal to infinity to a finite distance somehow. So instead of going to infinity, we want to bring it at a finite distance. So that this will be u equal to u naught, this will be, u equal to u1 up here, then I'll get here u equal to u naught. So we would like to bring this, so this is, so to say, r equal to infinity, this surface. And the question is, how do we find this surface up here? That's what we're trying to do. So we just go ahead up here, we write down the metric in terms of u coordinate. So we eliminate t. T is going to be equal to u plus r, therefore ds squared will just look like minus du squared minus times du dr. And when I take dt squared as du plus dr squared, I get a, because of the minus sign, I get minus dr squared, so that cancels this. I'm just left with minus r squared d omega squared. So this is the metric, and this is the same Minkowski metric, signature minus plus the known, and it is really the same flat metric up here. And now what we want to do is to go to infinity at along r equal to infinity along a u equal to u naught. So we introduce a new coordinate, call it omega, which is 1 upon r. So omega equal to 0 at r equal to infinity. And the idea is that we would like to express everything in terms of now u equal to constant, theta equal to constant, phi equal to constant, and r going to infinity, which is the same as omega going to 0. So that's what we're trying to do here. So this r equal to infinity is going to be the new coordinate omega equal to 0. So we want to get away from a coordinate which is not very useful for us, r, and we want to bring in a new coordinate which is just 1 upon r, so that we can do, so that omega equal to 0 would be the boundary that we are looking at. So when I do that, I just get here ds squared minus du squared minus du dr. You just substitute and you get here plus twice du omega upon omega squared, and r squared just becomes 1 upon omega squared. That is this r squared is 1 upon capital omega squared because omega is 1 upon r. So we find this Minkowski metric, and of course the problem is that if I take the omega equal to 0 limit, these metric coefficients blow off. It is just a reflection of the fact that if I go out to infinity along r equal to constant, u equal to u naught and r equal going to infinity, and if I look at longitudinal geodesics, for example, theta and phi, then the distance between them is growing linearly, just a straight line, and therefore that distance between them becomes infinite, and that is the problem that is happening here. So the metric is always bad at r equal to infinity, because r equal to infinity is not a part of the manifold, so it's not a good coordinate. R is not a good coordinate at r equal to infinity. So what we do now is really that we introduce a conformally rescaled metric. It's a mathematical metric, but it has the same physical information as a physical metric. So we introduce a new metric, which is conformally rescaled, which is rescaled by a factor, so which we call ds hat squared. And with this, just take it to be equal to omega squared ds squared. So omega is called conformal factor, and that was just the coordinate 1 upon r, if you like. Now, then the statement is that this looks perfectly fine. That looks like minus omega squared du squared plus from here plus twice du d omega, and then omega 1 upon omega squared cancels, so I get d omega squared. So d omega squared is just a unit two-sphere metric. It is just d theta squared plus sine squared theta d phi squared. d omega is perfectly well defined. Therefore, at omega equal to 0, which was the r equal to infinity, so r is a bad coordinate when it takes infinity value. So now omega is a good coordinate at that boundary, and then we find that at omega equal to 0, this term goes away, and I'm just left with du d omega times d omega squared. Now you might be first worried that if this term goes away, that means the metric becomes degenerate, but that is not the case. You can just see that this is du d omega, and therefore the metric is actually not degenerate. If you like, I got theta phi directions. In the theta phi direction, the metric is just unit two sphere metric, there's no problem. In the RT directions, okay, which is the same as u omega direction, the metric will take the value 1, 0, 1, 1, 0 in this d omega direction. This is du d omega, that's what it looks like. And therefore we can see that here it is not degenerate, right? Because its determinant is not equal to 0. Okay, so this metric is perfectly well defined at omega equal to 0. So the statement is that we have AB regular. And does have signature minus plus 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 as before. So we haven't changed the signature. All we have done is to absorb the bad behavior of the R coordinate at R equal to infinity. It's nothing. It is badly behaved because at R equal to infinity by conformal rescaling with respect to this omega. So we get this boundary very well. So this is the boundary that is written up here. If I were to draw a picture that we often draw, like here, where every point is a two sphere except this line. This is R equal to 0 line. The origin, every point here is just a point, R equal to 0. But every point here, R equal to R naught, is a two sphere of radius R naught. So if I draw that, then what I'm doing is, what I did up here is the following. U equal to U naught, where this null raised, and I've added the endpoints of this null geodesics, and this is, thus I obtain a surface up here, and this surface is just omega equal to 0, at which the null geodesics end. So I found, so to say, the final resting place of all null geodesics. Every point up here represents the endpoint of one null geodesic. That is what this is. And this is, Penrose, Roger denoted this by script I, and then it came to be known as scry. Scry just stands for script I. There's no. So this is a boundary. So scry, or let me call it scry plus, is a future boundary. Of space-time, which were obtained by conformal completion. And so I got a manifold now, this M hat. This is the Minkowski space manifold together with a boundary, which is I call scry plus, and I got a metric G hat AB, which is omega squared GAB, which is well defined everywhere. So M hat is a manifold with a boundary. What is the nature of this boundary? Well, this is U equal to U naught. This will be U equal to U1. And each of these each of the points up here is a two sphere. Right? Each of these points up here is a two sphere up here, labeled by theta and phi, up here. And therefore, the topology of this is two sphere times R. The R direction is a U direction, and two sphere direction is just the two sphere direction which goes around. In this picture, the two sphere direction you see everywhere here, and R and the real R direction there is just coordinatized by U. U goes from minus infinity to infinity. So this is the R direction is coordinatized by U, which takes values between minus infinity and infinity. So it's a cylinder, the boundary that we're attached to space-time. Now, of course, there's nothing special about going to future. We could also look at past geodesics, right? Just as we have done in future direction. So if you went to the past, then we will define V to be equal to T plus R, just as U was T minus R. This is going to be equal to V naught, geodesics up here. And again, I do this very similar construction, and I'll find just interchanging U and V. The only difference that happens is that instead of du d omega, you'll get minus twice dv d omega. And that minus sign is because V is given by T minus R, whereas U was given by T plus R. So you'll just get a metric up here again, ds hat square to be equal to minus times dv square minus twice dv d omega. All this is in the notes, so you can look at it, do all the algebra that you need to do. You can do it in the notes. So it's the same thing that we can define that this new metric is hat square, which is going to be given to us in this particular way. And therefore we can again also introduce here the pass boundary, and this pass boundary is called sky minus, and this is the pass boundary. Each of them has topology of S2 cross R, and this is what we have. Now these boundaries, as I have written down up here, they don't meet. Also u equal, the point up here, u becomes infinity. Here u goes to minus infinity. Here v goes to infinity, and here v goes to minus infinity. And so u equal to infinity, v equal to infinity, these are not points in our chart. Therefore these things don't meet. They just sort of, they come close, but they don't meet completely. And this is a picture we have. If time allows today, no, I probably don't allow. I'll do some a completion, which will also include these points, which is important not so much for black holes, but for many mathematical physics problems in general relativity. For example, the completion where these points are included was used first to show that in Minkowski space, Yang-Mills solutions to Yang-Mills equations have global uniqueness and existence. In other words, if you give me initial data, then I get a solution everywhere in Minkowski space. That was done by using this conformal compactification, which I will do perhaps next time. Okay, so I got this this metric up here. That's Minkowski. Okay, so we understand this Minkowski metric, and therefore now what we want to say is that, well, this is the boundary. So what we should do is we should look at the region. To come back to black holes, we should look at the region from which causal signals can be sent to infinity, to future infinity. Which means that I have to look at all the region from which causal signals can be sent out to infinity, so I have to look at past of this future infinity. And the question is, if I look at, so the region from which causal signal can be sent to infinity is precisely the causal past of this infinity. And then the question is the causal past of this infinity the whole space-time, or is something missing? If something is missing, then that is a black hole. For example, in this case, we're not done it yet, we'll do it today. In this collapsing case, up here, we'll have sky, which will look like that, sky plus. And if I look at the causal past, I will get with this region. And then the question is this the whole space-time? Well, no, because signals from this region, this region 2 up here, will never go to sky. All the future directed signals are falling to singularity. Therefore, this region is not in the causal past of sky up here. And therefore, this is a black hole region. So, to summarize, the idea is you try to construct what you mean by asymptotic region by adding a boundary to space-time. And then the statement is that when you add that boundary to space-time, you look at its causal past. Is it all of space-time? If yes, no black hole. If it is not all of space-time, then there's a black hole. In Minkowski space, of course, if I take this causal past, I look at this, I get the entire space-time. All these u equal to constant lines from u equal to plus infinity to u equal to minus infinity. I get entire space-time. So of course, there's no black hole in Minkowski space. So this is the idea.
So the problem in the black hole to do to get a complete future boundary in some sense, it comes from the geodesic incompleteness or something like that. That there's no conformal rescaling of the metric in the black hole region that allows to glue a future boundary there in any way.
Right, but I mean the thing is that we look precisely here at outgoing null direction, and the statement is that these outgoing null directions will not reach here.
They would even
will not even reach here. I mean, forgetting about whether you can put a boundary here, they will just not reach here at all. So therefore, you have sky, you look at past of sky. If there is a region from which there are no null geodesics is there. So it's quite up independently of the fact that we will not be able to certain conformal completion here. Even if you can do conformal completion here, the statement is that regions from here that will be another boundary up here. This is not.
So it is in principle possible, but it would not be the one reached by null.
By this null. Okay, so the statement up here is that I'm not saying that. Maybe we can come back again. I'm not saying that it's possible, but I'm saying that the logically the problem is different. The logically here is that from this region, if I look at the null rays, they all go into the singularity. None of them goes to infinity. And by looking at infinity and by going past up here, then the statement is that by looking at it past, we just miss out this region. Okay, maybe we should write down the next definition and then we can come back to this point again. Okay. So this is Minkowski space. So now this is the intuition. So we are on the notion of general notion of asymptotic blackness. So this is what you want to know. So we are given a physical space-time, like for example the Schwarzschild space-time, but it could be a star, it could be rotating star, it could be some any space-time that you give me. So given a space-time, a physical space-time, MGAB is said to be asymptotically flat. Infinity. If there exists space-time which is larger, M hat, J hat, AB, where M hat is a manifold boundary, M hat is a manifold boundary, and M hat is just equal to M together with the boundary. So it's obtained by adding some completion up here in M hat, such that where this is the thing, and with sky being a topology S2 plus R, and G hat AB is conformally related to the physical metric GAB, but only on the manifold M. So on the boundary sky here of M hat, G hat AB will be well defined, but G is not well defined because omega equal to 0, and this hat on equality will always mean equality in the boundary. Equality just at the boundary point scribe here. So such that omega is equal to 0 and grade omega is not equal to 0. Now where do these all conditions come from? I have to continue. But let's understand first here. So bigger manifold, this bigger manifold is precisely the one that we had here for Minkowski space. Minkowski space together with scribe is a bigger manifold. The conformal factor is omega up here. And then the statement is that the conformal factor omega was 1 upon r in physical space-time. The condition that omega is 0 but grad omega is not equal to 0 these conditions intuitively, so I should use another color. Intuitively, these conditions just mean, these two conditions just mean that heuristically omega is going up. If omega went to as 1 upon r squared, then grad omega is also 0, but grad omega will not be 0. If it went as 1 upon r cubed, then you just keep going. So this is what is it. And so these are the subtleties that I did not want to enter into when I talked about what happens here if you go to completion. So the statement is that the various conditions we are writing down now cannot be achieved during a completion which will also include this region. You still look puzzled?
So I just want to see the precise reason that if we would look at a spatial, well, some slice that contains a point in the manifold region, in region 2, and there we would try to look at a light ray that goes up to the singularity. That it is impossible to define a future point. So you're saying this is the reason why...
this condition and the condition I'm writing down now, more and more conditions I'm about to write down, those conditions will not be satisfied at this point. So
I see. And so the statement of the definition here is saying, I try to do this procedure to get as much of a future boundary as I can.
And that is the point.
And then I look at the past.
That's the point I'm going to about it. So for example, we're going to see, I'm running ahead of myself, but we're going to see in a minute that in fact these conditions that I'm writing down will imply that the boundary is not. So it's not. So it's not just one thing. The package cannot be, that conformal completion cannot be applied to this. You had a question?
Yeah, what does that equal sign with the squiggle on top mean?
Yeah. So this just means with a hat. It just means that this equality is just at points of scry, at points of the boundary of this boundary here. So and we'll use that just instead of writing every time that this is true only at scry. So this hat just means this equality holds. Equality. So this is equality. Equality just at points of scry, at the boundary. Okay. So I incorporate. I mean, it is somewhat surprising that at the end the definition is rather simple. I'll just tell you a little bit more about this. So we say that it can be such that you've got an original space-time and there's a conformally completed space-time. The boundary is just S2 cross R, and the metric is given by is conformally related. The conformal factor satisfies these particular conditions. Such that. So I'd now give some. I think there's only one condition. More. Yeah. Just. So we take Einstein tensor. This Einstein is a physical metric. This is a Ricci tensor, and this is the scalar curvature of curvature scalar, and so this is a definition. And Einstein's equation just tells us, and I put capital G equal to 1 in most of the lectures, so this is just equal to the stationary tensor, such that omega to the minus 2 times TAB has a regular limit. At the boundary scry. Remember, omega goes to 0 at scry. Therefore, omega to the minus 2 blows up at scry. So for this to have a regular limit, TAB, the stress intensity, should go to 0 at a certain rate. Of course, if you have vacuum solution, the stress intensity is identical to 0. So of course, I can put any n I want here. That will be regular. But for example, if you have Maxwell field in Minkowski spacetime, in this construction, if I put a Maxwell field, you can check very quickly using conformal invariance of Maxwell's equation that the stress and tensor of Maxwell field actually satisfies the condition omega to the minus 1 2 times t has a smooth limit to scribe here. Okay. So this is the condition. This is it. I mean, I'll just end of it. Now, the surprising thing is something that that Lucas was hinting at, that in this condition, I never talked about null geodesics. Okay, and I'm not talking. The first definition that Penrose wrote down was called asymptotic simplicity, and that definition required that and such that every null geodesic of the physical space-time has a future endpoint or a past endpoint, and the two things were called scribe plus and scribe minus. The definition that is given up here doesn't say any of that. Okay. And yet this is sufficient. I have to add some more conditions in a minute. We'll do that. This is sufficient to talk about both gravitational radiation theory or any radiation theory, and also construct the positive negative frequency solutions and Hilbert spaces in quantum theory, and also to talk about black hole theory, the whole thing about defined black holes and such things. So this is something that is not entirely intuitive, but it's just true that one can actually do this in this way. So the disadvantage of Penrose's definition was that in any practical, if I give you a space-time, it was virtually impossible. I mean, it's very difficult to check that this space-time is actually asymptotically flat if in fact you have to integrate at every null geodesic and see if it has an endpoint on this graph, right? It is just too much to do. I mean, and furthermore, of course, if you have black holes, then it is even not true, right? Because black holes, some geodesics fall into the black hole. So then he had a weakly asymptotically simple space-times, which had to incorporate the fact that in black holes something else is happening and so on. Whereas here, one doesn't have to distinguish it in, the weakly asymptotic, asymptotically simple and strongly asymptotically simple. One just doesn't talk about asymptotic simplicity. One just talks about this. And as I was telling you before, that there are complicated space-times in which you can, I mean, it's not trivial, but you can check that in fact it satisfies these, all these conditions. Not just standard space-time like Kerr space-time and so on, but many more complicated space-time. It's not trivial to know if a space-time is asymptotically flat. I'm not saying that by any means at all. Very often, to know if it is asymptotically flat, you have to have some intuition about geodesics, but that is just your calculational intuition. At the end of the day, all you have to do is to check that this is true. And now the idea up here is to say that, okay, if I got this thing, then we want to say that scribe plus is a part of the boundary such that no point, which is to the future, so no point of the physical space-time lies to the future of scribe plus. So in Minkowski space-time then, the statement would be that the total boundary would be this and this, and no point in the physical space-time is to the future of this. Okay. So therefore this will be called scribe plus in Minkowski space-time. And scribe minus is the same thing. You will be the opposite of that. Part of space-time such that no point of m lies to the past of scribe minus. So every point of m up here is to the, none of them lies to the past, and therefore this is actually scribe minus, as we just wrote before. I just write it in a different color now. And so this, now the idea would be, good. Now I know what I mean by asymptotically the boundary up here, and I can look at the causal past of this boundary, and I can see if in fact the causal past is all of space-time or it's not all of space-time. If it's not all of space-time, then there's a black hole. If there is all of space-time, then there is no black hole. So we seem to be almost happy, but there's a problem. The problem is that, Lucas might come and say that, well, wait a minute. I'm just going to attach a boundary. Here we're saying that given a space-time, I got a boundary such that. Lucas says that, well, I'm going to attach a boundary only to the future of u equal to u naught. Right? Sorry, to the past of u equal to u naught in Minkowski space-time. This is it. Because if I just look, I just stop my boundary up here, all these conditions are still satisfied because they were satisfied everywhere, so of course they are satisfied here. And then I'm going to say that, well, I got this boundary and therefore this is Scri plus. And now I want to say, wait a minute, look at the past of Scri plus. Does it contain, is it all of space-time? Is it not all of space-time? Of course it's not, because this part is missing. But clearly we don't want to say this is a black hole, right? And so this is a very simple point, but this was something that was missing in the original definition that Penrose gave. He never talked about completeness of Scri. And then Garrosh and Horowitz pointed out that completeness of Scri is something that is important. And it's important for this very simple reason, but we have to put that. And the reason I'm saying, emphasizing this so much, is because in many of the discussions of semi-classical gravity and Hawking evaporation, this is the point that people miss. They say something is there's the event horizon, but in fact it's not an event horizon, or there's a black hole. It's not, because Scri is not complete, so it really is not quite right. So let me just say now, so therefore, now next point. So I just explained in words. I would like to write it down because this is an important point. What I've said so far is that you have the notion of asymptotic flatness up here, but this is not quite enough because of this this silly problem, if you like, that Scri may not be complete. But you say, of course, you should just reply that, no, I wish, Lucas, come on, you can't stop here, you should have to go up here. But then Lucas comes back and says, what do you mean I cannot stop here? What is your condition which prevents me from stopping here? And now we have to write down this condition, not for Minkowski space-time, but for the general space-time. So what do we want to say? So the idea up here is that so remember that omega equal to 0 on Scri, and therefore, I'm sorry, yeah, let me say. Therefore, it is clear that an A, if I just define NA to be equal to grad A is normal to Scri. Now, the statement that, so I'm doing some in-between manipulation. So now I would like to know what kind of normal is it? Is Scri a null surface? Then the normal is also tangential to it. Is it a space-like surface in which the normal is time-like and Scri is space-like? Or is it a time-like surface? Then the normal is going to be space-like and the surface is time-like. What kind of is it? So what kind of normal is this? This is what we want to find out. And luckily, these little conditions that we have, they suffice to tell you what kind of normal it is. Namely, what we know is that we do conformal transformation. So I'm working my way to completeness. I just missed one step before, so I'm trying to fill it in, and then we'll come back to completeness. So we have to look at conformal transformation, namely, where G hat AB is omega squared times GAB. And therefore, I can express the curvature tensors of G hat in terms of the curvature tensor of G. Now, how do we do that? Well, first we began with the fact that I got a derivative operator. There is a unique torsion-free derivative operator which kills this metric. And similarly, there is a unique torsion-free derivative operator which kills this metric. I got a covariant derivative compatible with G and covariant derivative compatible with G hat up here. How are the two related to each other? Well, if I take any two derivative operators, then the difference between them is a tensor. That is the meaning of the affine connection, if you like. The difference between two derivative operators is really a tensor. And this tensor is some CABC times KC. And you can now substitute grad hat of G hat AB equal to 0. So just put here G hat AB, then write omega squared, then use the fact that grad of G equal to 0, you expand it all out, and you just find quickly that in fact CABC is a simple form. It is minus omega to the minus 1 times 2 times delta minus omega. Where the indices are raised and lowered with the metric g hat. So every time there is a hat, indices are raised and lowered with the g hat. So this is the case, and then we also know that the Riemann tensor is just defined by grad A, grad B of Kc. 2 times that is the Riemann tensor, R, A, B, C, D, Kt. And similarly, R hat A, B, C, D is defined by 2 times grad hat A. Same formula is true, so that defines that. Now I know what I can express grad hat in terms of grad, and therefore I can express the Riemann tensor here in terms of this Riemann tensor up here. Those of you who want to see some details in the textbook by Wald, there's an appendix which is called conformal transformations, where you will see the details worked out. But for our purposes, the details are not important, only the structure is important. The structure is that the metric g hat is related to g by a conformal scale factor, and therefore its curvature tensors are also related by a conformal factor. When you work it out, you find that R is equal to omega square R hat plus 6 omega times grad hat A and hat A minus 12 times N hat. Now at omega equal to 0, that's where what we're interested in. This term is not 0, this term is 0 because everything is assumed to be smooth. Therefore, the n hat A, the norm of this vector field is completely given by the value of R at special infinity. And what is R at special infinity? Well, we use Einstein's equation. If I use this Einstein's equation, RAB minus 1 half RGAB equal to 8 pi G, then of course, still stationary tensor actually vanishes at infinity sufficiently fast. We can check that this is actually equal to 0 at infinity because is regular there, and therefore it follows immediately that n hat A equal to 0 again, hat here just means equality at scri. So if I take the limit to scri, then omega is equal to 0, minus 12 n hat A is equal to this, but it's also 0, therefore I get this equal to 0. So therefore we conclude that scri is a null surface. So this just follows from the general definition. The scri is a null surface up here. Little side remark that if I had in fact a cosmological constant, if in fact the Einstein's equation was GAB plus lambda GAB is equal to 8 pi G, that's GAB. We assume the same fall-off condition on GAB, but then I also have this lambda up here sitting up here. Then you can quickly check that in fact R is equal to 4 lambda plus 8 pi times EAB times GAB. And this actually goes to 0 for a couple of reasons, because of the fall off of GAB that we assume, and also G up AB has an omega square times G hat AB, so that also goes to 0. And so we find here that R is equal to 4 lambda. So here in general we'll get here 4 lambda is equal to minus 12 n hat A. So that will tell us that n hat A is equal to minus lambda by 3. So if lambda is positive, then n hat A is time-like, then scri is space-like. And if lambda is less than 0, then n hat A is space-like, and therefore scri. This is normal, so if the normal is time-like, then the surface to which is normal is space-like. If the normal is space-like, then the surface to which it is normal is time-like. This surface is normal, it's time-like up here. So these are respectively the asymptotically de Sitter spacetimes instead of asymptotically flat, and asymptotically anti-de Sitter spacetime. In which, in one case, the null boundary is time-like, in the other case, it's space-like, and when lambda equal to 0, it is equal to 0. And this difference between space-like, time-like, and null is very critical in the radiation theory, and one of the reasons why things have been done to a great extent in the string theory literature for anti-de Sitter spacetime is because Scri is time-like there. If it is space-like, many of those constructions just don't go through. You do not have, for example, the DS CFT correspondence as you have for ADS CFT correspondence. And that is really quite related to the simple thing that the two things are quite different from each other. But for our purposes, we're interested in the null case, where lambda is equal to 0, asymptotically flat case, then this is. Now, so it is null. So we go back up here. We have to talk about completeness of Scri. And what we are seeing now is that normal to Scri is null, and null surfaces have the property that the normal is also tangent to Scri. Right? So since Scri is null, so it's also tangent to Scri. So now the statement is that we want to know what do we mean by completeness of Scri. This is the question that we are looking at. What is it? So what we now want to say is that Scri is complete if this vector field n hat A is complete. Now what do I mean by a vector field is complete? It just means this affine parameter mu defined such that this is equal to 1, then mu goes from minus infinity to infinity. That is what we mean by complete Scri here. So this looks well okay. So now finally we're done, but we're not. The reason is because this is still not quite okay. The reason is because n hat A is not canonical. You see, the physical metric is canonical. But to construct the G hat AB, I have to introduce an extra ingredient, which is the mathematical ingredient, which is omega. And I could choose one omega, and you could choose some other omega. And then when I choose these different omegas, since NA is grad omega, NA changes. So who is complete? Is my n complete or is your n complete? That is a question. So the question is really which n? Which n hat A? So this is the problem. Which n hat A are we going to say that is complete? And the answer to this is not, I'm just going to tell you the answer. If you have questions, I'll answer them, but I don't want to sort of tell how people arrived at this conclusion. But which n hat? Well, the idea is here is very simple, namely that look at what we have is this n hat A, and we can demand that this n hat is divergence free. If n hat A is divergence free, so first of all, we can always make, let me rewrite it. We can always make by conformal transformation. What are the conformal transformations that are allowed? Instead of big omega, I can use big omega times little omega. And little omega is smooth and non-zero. That's Scri. If I do that, then if an omega is equal to 0, omega prime is equal to 0, and the second condition that is non-zero is required because we want grad A omega to be equal to, not to be equal to 0, and grad A omega prime also not to be equal to 0, and that's what that is satisfied if little omega is not equal to 0. So we can always make this divergence free by this conformal transformation, and the statement is that, but you can just choose omega It is simple exercise, but you can just check that. We can choose omega such that grad hat A and hat A prime is equal to 0. So this is called, this choice is often called divergence-free conformal frame. This is often called divergence-free conformal frame. It's a choice of omega. We're restricting our choice of omega. And then the restricted freedom is just omega goes to omega prime, which is little omega times omega, such that union of little omega equals 0. In other words, little omega is constant as you go up and down scry. So little omega is a function of only theta and phi angle and does not depend on u. Does not depend on u, it's just this ln, and that's because n ln is just the vector field n hat A. Vector field n hat A is just d by du vector field. The vector field which goes up and down. So there is a subtlety. I mean, the original definition that was given by Penrose was in terms of asymptotic simplicity and weak asymptotic simplicity. It had some, I mean, a slight conceptual limitation. Practically, it is also limited because it is difficult to check that all what happens to all my geodesics. But when once that is done, then we got scry complete. So then the statement is that now we are almost there, except for one last subtlety, but we're almost there now. So the statement is now that we say that a spacetime MGAB, an asymptotically flat spacetime. So spacetime which satisfies all these conditions is said to be asymptotically Gaussian. It's called asymptotic Minkowskian because it just to make sure that we are not forgotten part of scry. In Minkowski space, our construction gave us complete scry, and in general also we got this complete scry. So it's said to be asymptotically Minkowskian if in a divergence-free conformal frame n hat A is complete. This ensures that I should not have forgotten part of space, been careless and just got part of scry plus. I worked hard enough to get all of scry plus. That's what I had to do. Again, that is to say, divergence-free conformal frame means grad hat A and hat A equal to 0 at scry. And the point is that if in fact if n hat A is complete, if n hat A is complete, and then you define omega prime to be equal to omega omega, such that this is also true. So that n hat prime is also divergence free. Then you can check that completeness of implies completeness of n hat A prime. And the reason just is because u, the affine parameter of n hat will be related to the affine parameter of n just by a function. So it's just a function of theta and phi, and therefore if u goes from minus infinity to infinity, u prime also goes from minus infinity to infinity. So we don't have any problem. So this is just a parenthetical remark up here, which completes here. Namely, that I said in a divergence-free conformal frame, n heading is complete. And the statement is that once you have done it for one conformal frame, you can stop. You don't have to worry about whether it is true in all conformal frames which are divergence-free, because it's automatically true in every conformal frame which is divergence-free.
Sorry, what was the initial completeness for the
Yeah,
vector n?
yeah. So n hat complete. It means its affine parameter u goes from minus infinity to infinity, where u is affine parameter. It's equal to 1. So it's affine parameter. So that's completeness definition of any vector field. Just does without even a metric, right? I mean, if you just go manifold and a vector field, you say is it vector field complete? If in fact its affine parameter runs from minus infinity to infinity. Yeah, affine parameter does not need a metric. Just like,
Can I ask you a quick question
Yeah.
about that also? That makes it sound very coordinate dependent.
which one?
The definition of completeness in terms of you put an affine parameter on it and you ask for the full range. And so is there a more coordinate independent geometrical way of saying that completeness?
This is the practical way of talking about completeness. So a vector field is complete if its affine parameter is complete. I think if you have, for example, vector, in the Riemannian case, you can say the length of the curve is complete, integral curve is complete. In the null case, we cannot say that. I don't think it's coordinate dependent in the sense that
I kind of understand that it's not.
because it doesn't depend on coordinates of the manifold. It is some structure. Given any vector field, it is born with a family of affine parameters. So in that sense, it is not. It's just like given a metric, it is born with a torsion-free derivative operator. So in the same sense. But yeah, you're right. I mean, I think. But this is the thing that we use in ordinary differential equations, for example. Okay, so we're done up here. Yeah, I think that I should. There's one small point. So now the question is, what is a black hole? So I'll just finish this little thing next time. So the black hole is really, you're given this asymptotic in Minkowskian space-time. You look at Scri plus, which is all the future points of the boundary. You look at their complete past. And the question is now, is the complete past all of space-time, or is it not all of space-time? If it is all of space-time, we would like to say that there is a black hole. There is no black hole. If it is part of space-time, then we would like to say that there is a black hole. But I have to confess that there is still one small caveat, which I'll fill next time. It is a quick one, therefore I hope to do it today, but we don't have time. I'll fill that next time. It's a very small caveat, and then we'll be done. Then we'll have notion what a black hole is, and this is a notion that is used everywhere, right? And when people talk about black hole, could be, black hole mechanics, black hole, and then asymptotic de Sitter, asymptotic flat, asymptotic de Sitter, etc., etc.